The title of Professor Stein lecture is The Cauchy-Szegö Projection in Several Complex Variables, LP Estimates.
So, thank you very much. And of course, it's a great pleasure to be in Wrocław after all these years. And I was not, unfortunately, in Wrocław when Andre was alive. And he was a great guy, as all of you know. I also want to thank Mariusz and Bartek for the invitation, the possibility to come here, and also for making my stay so nice, arranging everything. So I also want to say that I'm working with them, but more precisely, I'm listening to them explain some very interesting work of theirs, very interesting work, and I'm trying to understand it. So I'm not going to talk about that today. I'm going to talk about some other work that I'm involved with, which is joint work with Loredana Lanzani, having to do with the Cauchy-Szegö projection. Now, Professor Blocky spoke about the Bergman kernel and the Bergman projection. There is some relation between the two, some analogies, but the kinds of problems we're going to, one is interested in, at least here, are quite different. All right, so basically, one starts with the Cauchy-Szegö projection in one complex variable for the unit disk, and that's, you might say, the most fundamental operator in classical harmonic analysis. It's the Hilbert transform, or the Cauchy transform. But then one is interested in what happens if that domain is replaced by, the unit disk is replaced by a domain in several complex variables. And what is the corresponding theory? And it becomes quite different. So let's talk about that. So this is the outline of my talk. So first, I'll just say a few words about the classical situation. Then more about just one dimension, but that's not really the focus. The main focus will be the situation in n complex variables, one general n. So now, the starting point is the Cauchy integral. So if you have a domain omega, let's see if I can use this pointer, a domain omega, you can define the Cauchy integral, a domain with a sufficiently regular boundary, by integrating a function on the boundary, and the function at this stage can be quite general. It doesn't have to come from an analytic function. So from the function on the boundary, you produce this way a function which is holomorphic inside. And then the interesting operator to form is to take this function which is analytic in the interior and to pass to its boundary values whenever those exist, and they exist under very general circumstances. And that's sometimes called the Cauchy transform. All right, so what are the obvious properties? First of all, that the Cauchy integral is, of course, holomorphic in the interior, and that this, that this Cauchy transform reproduces holomorphic functions in the sense that if you had a function little f, which arose from a function capital F, which was holomorphic in the domain, and little f was its boundary values, then if you formed the Cauchy of little f, you would get back capital F. Now, related to this is the Cauchy-Szegö projection, which is defined now in a different way. So one starts with the L2 space of functions on the boundary, with, let's say, the induced Lebesgue measure. And one looks at the subspace of that, of those functions in L2 which arise as boundary values of holomorphic functions. Or to be precise, one takes holomorphic functions which are continuous up to the boundary, and one takes the restriction to the boundary of those continuous functions, and one takes the closure in the L2 norm, and that gives you the Hardy space, the boundary Hardy space. All right, and then one takes the orthogonal projection on this subspace of L2, and that's the definition of the Cauchy-Szegő projection in this case. All right, now why is this interesting? For example, still in one complex variable for the unit disk, both of these two objects are the same, the Cauchy integral, or the Cauchy transform, and the Cauchy-Szegő projection. And of course, they have a very nice interpretation in Fourier analysis. So if you start with a function f and its Fourier expansion is given this way, then the Cauchy transform and the Szegő just cut off the negative frequencies. And from that, it's obvious by Plancherel's theorem that this is a bounded operator in L2. It's a projection. From that, it is obvious. And then there's the classical theorem of M. Rees, which states that this is a bounded operator in LP. So that's the starting point. So next, more about one dimension. So the first question is, can you generalize this to domains, not the unit disk? So the thing to do here is that if the boundary of the domain is sufficiently smooth, and sufficiently smooth here means that it's C1 plus epsilon, where epsilon is positive, then one can prove, that there, of course, there is a Cauchy integral, and there's a Cauchy-Szegő projection, and the two are the same except for an error term now, which is a smoothing operator. So from the point of view of LP theory, it's a negligible operator. It smooths essentially a degree epsilon, where epsilon was the epsilon of the smoothness of the boundary. And now, there is also maybe the best way to prove this is by a simple observation that Kurtzman and I made long ago about the relation between the Cauchy integral and the Cauchy-Szegő projection. And there's a multiplicative relation where A is the difference of the Cauchy that should be equals. A equals C star minus C. So you look at the Cauchy integral as an operator, and you take its formal adjoint, and if this is actually an almost trivial identity. But if that difference happens to be small in some sense, or smoothing, then you can invert this I minus A, and you can express S in terms of C and deduce from properties of C the properties of S. Okay, so that's what's being said here. Now, where am I? So what is the minimal amount of smoothness that you can make things work for? Now this becomes more interesting, even though it's still in one complex variable, but it's basically been done quite a while ago. So the first answer for the Cauchy integral, the limit is essentially at epsilon equals 0. There are different ways of expressing this. So for example, instead of C1, there's the condition of being Lipschitz, and that's a very famous theorem of Kaufman, McIntosh, and Mayer, starting with earlier work of Calderon, who proved that in that case, the Cauchy integral is a bounded operator on LP. So that's the result there. Now, one may ask, what's the result now for the Cauchy-Szegő projection? So here, the result splits into two parts. If the domain is of class C1, then it is still, that's the result up here. Then it's still bounded on all the LPs. But if it's merely just Lipschitz, then it is bounded on a range of P's, which always includes F 4/3 and 4, but the range is dependent upon the geometry or the degree of the Lipschitz bound. And all of that is a series of results which culminated in this last paper some time ago of Lanzani and myself. But now I want to say something about this result in one complex variable, and then we finally come to several complex variables. So there are two ways of proving the result for the Cauchy-Szegő projection. One is to use this should be conformal, not this to use conformal mapping. So suppose you have a simply connected domain, which is reasonable. We can have a conformal mapping from the unit disk to that domain, and you can carry over the theory of the unit disk to that domain, and it leads to weighted AP classes, but for the standard Cauchy integral. And the second one is to use this identity, which I showed you before, which I said this simple identity, and to try to get the difference between the operator and its adjoint. All right, so here is a very quick discussion of conformal mapping, and here's the second approach. All right, so that is all I want to say about one complex variable. So we're essentially that problem is close to being finished in one complex variable. But now we come to the problem of several complex variables. So here is the question we pose. The question is up here. Suppose we start with a domain in Cn. What are the minimal smoothness and geometric conditions to be imposed for the Cauchy-Szegő, so that the Cauchy-Szegő projection is bounded on LP? So we start with a domain in several complex variables. We has some reasonable amount of smoothness, but we want to talk about somehow the least smoothness possible. And we define this orthogonal projection. So it's certainly bounded on L2. We want to know when it's bounded on LP. Now, let me mention, to make it interesting, why at first this seems so challenging. So the problem seems so challenging, but like many other problems, it turns out to be not as difficult once it is done. All right, so the first problem, I would say, is the failure, looking at the analogies with one complex variable, is the failure of conformal equivalence. That is, as is well known in several complex variables, that if you could have a domain that almost looks, let's say, like the unit ball. It's C infinity very close to it, but it is not holomorphically equivalent to the unit ball. There are all sorts of obstructions. So that's one failure. The other, well, that's one of the failures. So you cannot hope to use anything like conformal mapping in proving anything general. Now, then there's another thing which occurs only as soon as dimension is greater than 1. That's the notion of pseudo-convexity of a domain has to enter. So That is in almost every problem in several complex variables. Now, pseudo-convexity is a kind of a convexity which is holomorphically invariant. That's a convexity of the boundary. So on the boundary, if it has a tangent plane, then the tangent plane has real dimension 2n minus 1. But there is a subspace of dimension 2n minus 2 of the tangent space, which represents somehow the complex or holomorphic directions. And this pseudo-convexity is a convexity only in those directions, roughly. All right, so that has to play a role. Now, pseudo-convexity is a condition which has to do with second derivatives. So it's very natural that the minimal kind of smoothness should be near C2 and not C1. And that comes up in many problems, but this is just an indication. All right, now here's the third difficulty. I mentioned this approach, the identity P, which means that in order to study the Cauchy-Szegő projection, we want to study the Cauchy integral and know nice properties. So let's find a Cauchy integral. Now, the problem is that as soon as we are in several complex variables, there are infinitely many variants of the Cauchy integral for a reasonable domain. And almost no variant, one single variant will do the job. Oops, what has happened? Oh, I pressed something by mistake.
Shift, dałem shift, ale coś nie chce.
Yeah, I pressed something by mistake. I may have pressed something by mistake. All right. So these are three. Now I want to mention a fourth problem. A fourth problem is that there is if the domain is convex, it's strongly pseudo-convex, and is smooth, have certain degree of smoothness, C3 or more, then Pfefferman, in a very famous classic paper, studied the behavior of the Bergman kernel near the diagonal, not on the diagonal, but so, and he also studied the corresponding behavior of the Cauchy integral. So what the kernel of that operator is. And now from that study, one can, by using sort of the Calderon-Zygmunt paradigm, using that, one can prove the LP boundedness of the Cauchy-Szegő projection, but only when the domain is sufficiently smooth. Because as soon as the domain is not smooth, then this asymptotic development for the Cauchy-Szegő projection doesn't work. So these are some of the challenges. Now, let me tell you what the theorem is, and then I will just say something about the proof. So now, I think I've tried to tell you that the challenge of minimal smoothness is at 2 degrees of differentiability. So we're going to take domains which have a boundary which is of class C2, which means that they're given by a defining function which is of class C2. There are many different ways of saying it. Okay, so it's a domain which is of class C2, and so there's a notion of pseudo-convexity, but also there's a further requirement here which can also be in some sense philosophically justified, of strong pseudo-convexity. Strong pseudo-convexity is that the corresponding Hermitian quadratic form, which gives you the convexity strictly positive, definite, as opposed to, at each point, as opposed to being just positive, definite. All right, so the thing is that, the theorem is that the Cauchy-Szegő projection is bounded on LP for, you might say, the classical range on P's. Now, to make this thing precise, which I haven't made precise, I have said, well, you take your domain and you define L2 by taking the induced Euclidean measure. However, and this turns out to be very important because it arises in the proof, you can take another measure on the domain, and with a density omega, d sigma is the the induced Lebesgue measure, but you can take one omega. For example, where omega, let's say, is a continuous, strictly positive function on the boundary. Of course, then the various LP spaces are the same, but the inner products are not the same, and therefore the orthogonal projections are not the same. So there is a Cauchy-Szegö projection for each density or for each such measure. And there's no simple relation between those Cauchy-Szegö projections. So in principle, they're all interesting. And they're particularly interesting because while you might say this is the L2 space with this thing is the natural one, there's another one for which the proof works first, and one needs it, a very special measure, which we call the Leray-Levy measure, or the Levy-Leray measure, which is equivalent but not the same. So one needs to know it for that first. All right, so that's the corollary. So when this is the Leray-Levy measure, we start by proving it then and finally deducing it from that case. All right. Now I'm going to just mention what are the 7 steps to reaching our goal. All right? So the first step is to recognize what is a Cauchy integral in the case of more than one complex variable, since, as I stressed, it's not unique and there are so many examples. So what would we, first of all, require as necessary conditions to call an operator a Cauchy integral? It should be an operator with a kernel, which depends on W is integrated on the boundary, and let's say to begin with, we're integrating with respect to induced Lebesgue measure. So you have a kernel, functions, for that defines this. And what you want is that one of the critical things you want is that for any reasonable, let's say continuous function on the boundary, what you produce is always a holomorphic function, okay? And the second thing is that what you get, that this operator reproduces holomorphic functions. In other words, if F arose as the restriction of a capital F to the boundary, and a capital F was holomorphic and continuous up to the boundary, then C of F gives you capital F. And the third thing, which is somewhat vague, but I'll state it anyway, is that this be explicit in some sense. Because if we drop this this is already satisfied by the Cauchy-Szegö projection. And therefore it will be to say we're going to use this to study the Cauchy-Szegö projection would be nonsense. So we need to start with something that we really know that is explicit so that we can already know that this operator, let's say, is bounded on LP. All right. So it turns out that there's a very good formalism that allows us to do the second and third thing we require, but not the first one. And that's called the Cauchy-Fanta formalism. And it comes about as follows. We have to start with a one form. There it is, with coefficients capital GK. And this is a one form G, capital G, and then from this capital G, we form this little g, which is sort of taking this as vector and taking a complex inner product with the W minus Z. So it's written up here. And notice there are no complex conjugates here. So as a function of Z, we have, well, anyway. And the crucial thing, what we will need, because this will come up as a denominator, is that it is non-vanishing when W is on the boundary and Z is in the interior. And now we form this expression. So what is this? G is a one form. And now we take D bar W, so that's of G, which now makes it a two form. And now we raise it to the power n minus 1. That is by wedging. We wedge this 1 form or 2 form with itself n minus 1 times. So this is a 2n minus 2 degree form, and this is a 1 degree form. So altogether it's a 2n minus 1 form. And so therefore we can integrate that on the boundary against the function. But of course here's the fundamental denominator that has to enter. And the factor 1 over 2 pi to the n. And the basic fact is, so that's the Cauchy-Fanta. So whenever we have these functions gk with this property, we can make one of these integrals. And of course, we can find infinitely many such functions. But let me just make the following point. There's only one such integral when n is equal to 1. So you can easily see that when n is equal to 1, there's a cancellation between the numerator and the denominator, and the only thing that's left over is the usual Cauchy integral. But otherwise, there are infinitely many. And so the final important question, a preliminary question, that is the question about the Cauchy integral, is to construct one where the property 1 is satisfied, and that basically requires that this kernel is holomorphic in Z, and because because of the nature of the Cauchy-Fanta integral, it requires that you have a singularity on this boundary point. At each boundary point, W, when W is equal to Z, that is when you're on the boundary, and that forces already pseudo-convexity. So let me just go back here. But it has been, only when the domain is pseudo-convex, and it has only been done really in the case when it's strongly pseudo-convex previously and sufficiently smooth, first of all by Henkin and Ramirez, and then by another method that came later. So let me just say something. I won't go into details of how you can construct this Cauchy-Fanta. The basic one form that we want is just gotten as follows. You take the rho is the defining function for the domain. That's the function which is 0 on the boundary, is negative on the interior, and is positive in the exterior, and whose gradient is non-vanishing, is a function of this kind. That's a defining function, and whose gradient is non-vanishing on the boundary. And now we form this expression, and that is obviously a one form, and that's going to be our G. And now, if we do that, then little g is given by this expression. And notice that as a function of z, it is a quadratic polynomial just in z. So it is visibly holomorphic. And the non-vanishing is given by this, because this is essentially an expression of the strong pseudo-convexity. And that is the right thing that we want for G when Z is near W. But when Z is away from W, and we still need to have this expression, this is a real problem. And then we have to construct this. And there are various ways of doing that. And this involves solving some kind of D-bar problem or construction of some holomorphic function. Anyway, this has been done when the domain is sufficiently smooth. And we can actually carry this construction out in the C2 case. So I'm not going to say anything more about this construction, but that has been done. Now, here is the first obstacle. The first obstacle is that when we look at our Cauchy integral, which I think I should go back to here, where is there is the Cauchy integral. See, and the singularity of this thing, which we would like to consider as some kind of Calderon-Zygmunt integral to try to prove that it's bounded on LP. Well, notice something about this G. This G, I've written it down here. Notice that as a function of W, as a function of Z, it's very nice. It's quadratic, linear and quadratic in Z. But as a function of W, we started with a rho, which is of class C2, and now we've eaten up all the smoothness of rho. And rho, we get only a function which is continuous in W. It's very nice in Z, but it's now there's no singular integral theory which deals with kernels which do not have some smoothness away from the diagonal. All the usual Calderon-Zygmunt paradigm or the T of one theorem of all of these have some kind of smoothness. So that is our first, that is our first obstacle. There is our first obstacle. So instead, we do the following thing. The lack of smoothness comes about, because these second derivatives are only continuous. So for every fixed epsilon that is sufficiently small, we find another matrix of functions of W, which let's say is of class C1, but we make a small error. And let's just see what happens if we substitute this for that. Okay, so then we get a different denominator, but the denominator is in size not very different, but at least now we're getting things which have some smoothness in W. And we get now a Cauchy integral which is depends on epsilon and has some smoothness in W. And now for this one, for each fixed epsilon, we can try to prove the regularity, that the LP boundedness of this Cauchy integral, but ultimately we will have to pay the price, because ultimately we will really want to let epsilon tend to 0. And then the smoothness will begin to disappear and will be reflected in a very serious problem. All right. Now, so let me just say very quickly how for a fixed epsilon one proves, but this is using the pretty standard paradigm nowadays. One has to find a distance on the boundary. It's not the Euclidean distance, but it's the space of what's called homogeneous type. And the distance is naturally given by taking the denominator, that gives you the square of the distance, the absolute value of the denominator. And that's the same as the denominator with the epsilon approximation in there, because they are equivalent for small epsilons as far as the size is concerned. So we can take that as the space of homogeneous type, and then we can try to verify the basic properties of the so-called T of 1 theorem, which will give the boundedness on L2 and LP. And what we have to verify about this integral are three things. We have to do the cancellation. There are certain cancellation properties which are expressed by taking bump functions, having the operator act on these bump functions, and seeing that they satisfy the kinds of bounds they would satisfy if the operator was bounded, but just restricted to bump functions. Bump functions are functions supported on small balls which have some degree of smoothness. All right? And the second one is we want to know that not only this operator, which we've written down, which is sort of complicated looking, we need to have the same thing for basically its adjoint. We need to know what the dual operator is. And finally, this regularity of the kernel, which I said we needed some smoothness. And now that we have already put in there. So let me just say something about how we test this operator on bump functions. It turns out that there's a very nice identity that holds, an approximate identity, that holds when n is greater than 1, but does not hold when n is equal to 1. Basically, it says that this kernel, which is the kernel of G, which is really G sub epsilon raised to the power here, n, not n minus 1, is a derivative of the corresponding kernel with the power n minus 1. So it's, and then you can do an integration by parts, and then you can have a nice expression for functions f which are, let's say, of class C1, and typically a bump function is of class C1. So you can use this to make estimates if you have this integration by parts form. This is a version of Stokes' formula applied to here. Now notice that in n when n is equal to 1, this formula, this somehow can't be true because this would be taken up by the logarithm, and the logarithm doesn't scale right. So, all right. Now, in order to get to the adjoint, you want to simplify this, and that's where you are forced to introduce this Leray-Levy measure, which I will say very quickly about. The Leray-Levy measure is basically given by this form where rho is a defining function, and the factor 1 over 2 pi I. So for every defining function, there's a corresponding measure, and it turns out that this measure is the same as the induced Euclidean measure, except for a factor which, again, involves the second derivatives, and so it's a continuous factor, and the strong pseudo-convexity makes this factor strictly positive. So we're dealing with that kind of a measure. All right. And the main point is that once you introduce this measure, then the operator is very simple. It's just given by dividing by this thing, which has the epsilon, raising it to the nth power, integrating on f, plus a technically negligible, I won't get into this, but it is negligible term. And therefore, the adjoint, you can just read off the adjoint, but the adjoint has to be taken with respect to this measure, not with respect to the induced measure. Then the adjoint becomes the same expression, except z and w is reversed, and complex conjugates, so you can just read off what the adjoint is. All right, so far so good. We have found some, actually a whole family of Cauchy integrals, and now we want to start to do some work with that. We also have the regularity of the kernel, because I have imposed that regularity with a price that we're going to have to pay for. All right. Now, the next step is to realize what the problem is. Now, if we go through with this construction, and we see what happens when epsilon tends to 0, we see that we are in these estimates involving the, first, we are involving the derivative of the function here, and since it's of class C1, it gets the derivative of this approximating function gets worse and worse, because if it remained bounded, it would mean that our defining function had, for example, one more derivative. So there's got to be, this means that in the general situation, in almost any norm that you take for this operator, it tends to infinity as epsilon tends to 0. So now, how are we going to save ourselves from this difficulty? Now we're going to do something as follows. Yes, there is something that goes wrong as epsilon tends to 0, but we're going to get around this point by, at every epsilon, we're going to truncate our operator in the sense of taking the kernel, the original kernel for C epsilon, and restricting it to a narrow region about the diagonal. And the narrow region is given basically, remember that the size of the absolute value of G epsilon of WZ is the square of the non-isotropic distance that's being used here. So it's basically where the distance between W and Z is less than or equal to sigma, but it's done in a smooth way with a characteristic function. So there, we're going to write it as this part plus an error term. And then we will begin by taking epsilon small. That's our first impulse. But then we will have to take sigma small, because epsilon is small, and the smaller we take epsilon, to be the smaller we will have to take sigma, and then we will have a remainder. So well, let's see how this thing, okay, so I'm first of all going to say to you why the estimates for the truncation, and you can begin to believe this, are better. So epsilon will be fixed, and what can we say when we make sigma small? All right? That's sort of believable, but let's go on and state them anyway. So first of all, there is the following proposition. So these are the more technical things that have to be proved. So for any fixed epsilon that is small. Now, the norm of the operator C sub epsilon is in principle big. But then we can find a sigma which is small, smaller than sigma, depending on epsilon, such that the corresponding truncated operator is bounded in LP, but it has to have a bound which cannot be any better than MP, where MP is the standard kind of behavior of a bound up to a constant here, that it blows up like 1 over P minus 1 as P tends to 1, and like goes to P, that's the dual amount, as P goes to infinity. So that's this. Now, you might ask, as long as I'm making things better, why can't I make, so this to understand what maybe is going, a little bit of what's going on here. Why can't I take sigma so small to make this norm for any fixed epsilon as small as I wish? Why is there an upper bound? Well, you can see that very simply in a toy model case. If you take the Hilbert transform, you take the kernel of the Hilbert transform and you truncate it at a very small size, can you make the norm of that transform small as you make the truncation small? No, you can't, because of dilation invariance. A truncation in a small size, the norm for the truncation in a small size is the same as the norm at the unit truncation, which is the same as the norm for a large truncation. Then you can make that norm go to infinity, and you get the norm. So you of the whole Hilbert transform. So you can't do any better, but you can do at least as well as that. All right, now the next thing that is really the crucial thing is the following. Now, we're not just going to truncate the operator, but we're going to have to know the important difference, you remember, at the simple inequality that we had before, where you have to compare the operator with its adjoint and make that small. So here is the point. Suppose I want to make the operator small. We can make the operator, well, we can never get rid of this MP. We could hope to make it smaller, let's say if we were very lucky, by epsilon. It turns out not even epsilon, but epsilon to the 1/2. So the point is that for every epsilon, by making sigma sufficiently small, we can get this. And what is the only thing that matters now is that for our fixed P that we're going to be working with, we can make this thing strictly less than 1. So that's really what matters. But what comes out in the argument is epsilon to the power 1/2. Actually, what comes out of the argument is a little bit better. It's epsilon to the power alpha, but alpha has to be strictly less than 1, even though you might think to begin with it should be okay. So that is what is being said here. Now, what are the lemmas that make it possible? So there are some simple things that already indicate why we would gain something. So I'm just stating these lemmas to give an idea that indicate that for y for a fixed epsilon, by taking sigma sufficiently small, we can reduce things. So here's the first lemma. The first lemma is just the basic difference of the denominators, which was bad in W. But this now, when you really look at it, you can get this, you can get it this way, because what one really had was this, and now we just need to make this thing small to compensate for that. It is as simple as that. So that's what gives us this inequality, as long as we are in this region. Now, and the second thing is the following thing. If the domain were of class C3 and not class C2, then there is this miraculous property, which was already observed some time ago, that this is almost symmetric. In other words, in the case of the domain of class C3, one could prove that this is less than this distance raised to the 3rd power. So essentially, in the class C2, because of the modulus of continuity of any continuous function has a modulus of continuity, we can gain an epsilon by making this thing. That is not a difficult thing. So here we're playing with the modulus of continuity of the second derivative of rho, which we could only assume is continuous, and here we're playing with this inequality. Well, this gives us a sense that we're going to be able to gain something. So now let me just show you how the argument will work. So what I've suggested is that you take this Cauchy integral, which has the epsilon in it, and truncate it, and then there's going to be one part of the truncation which will have a small norm, but there's be still left over another part of the truncation which has a large norm, but it has the following saving grace. Remember, what is our truncation? We're truncating around the diagonal. So what's left over is an operator which is supported away from the diagonal. So by the very nature of that operator, there is no singularity. The kernel is a bounded, in fact, a continuous function. Of course, the bound of that function gets worse and worse as sigma gets closer, that is, as you're getting closer. But so an operator of this kind has an advantage. It maps L1 to L infinity, trivially, because it has a bounded kernel. And hence it maps any LP to any LP prime. Of course, the norm is going to blow up as epsilon goes to 0 as sigma, but we're only going to fix some epsilon and then fix some sigma. So let me just show you how we finish the proof. So we start with our projection in this case of the where we're dealing with the Szegő projection for the L2 space with the Leray-Levy metric, where we can read off very quickly what is the adjoint of our Cauchy integral. So let me just sort of finish by that. So what we begin is by writing, this is the simple identity that we had before. And now we decompose our C epsilon in this. And now our epsilon, which is this remainder, I said maps L1 to L infinity. Okay, but the bound of this operator blows up as epsilon and sigma tend to 0. Now, if we look at this thing and put this in there, then we get a more complicated version of this identity. But let's look in here. Here we've put these terms together. And now I've said that for every epsilon fixing P, and let's take first P to be anything between 1 and 2, we can make this norm of this operator in LP strictly less than 1. But we have this factor epsilon to the 1/2 or whatever, so by making this. So this operator here can be inverted as made its inverse is a bounded operator in LP by the Neumann series. And now let's see why this is now for that fixed epsilon and sigma a bounded operator on LP, because then that will force a C. But of course, we know that for fixed epsilon, this Cauchy integral is a bounded operator. Let's take this term. This, starting with a P less than 2, maps, since it maps every LP space into every other LP space, maps the LP space to L2. This Szegő operator maps L2 to L2, but LP is inside, L2 is inside of LP. So this maps LP to LP for P less than 2, and the same for this. So that would prove the theorem. So I think I'm past my time. I could say some more, but this is the outline of the proof. And I think I'll stop here.
Are there any questions, comments?
So I have a question.
Yes.
I haven't understood. So you don't go with epsilon to 0, do you?
Yes, you go to epsilon to 0 because that, what is the estimate for this norm?
This is good. Okay.
Yeah, that's why you
What
get.
about R?
But then R can be large. I don't care how large the norm of R is, but it's a bounded R. Look, we're trying to prove S0 is a bounded operator. So first we pick an epsilon and to try to make this thing less than the norm of this thing less than 1/2, all right? So that means that we have to pick a sigma sufficiently small, and the epsilon will, so that this becomes now less than essentially epsilon to the 1/2. So certainly by picking epsilon sufficiently small, we have made that less than 1/2.
Okay.
And because you have to fight against the other factor, which is M of P, the standard bound. So altogether, what we're making, first of all, is making the norm of this difference strictly less than 1. Then we can invert this operator in LP. And now you get two pieces which have very large norm, but they are automatically bounded, trivially bounded. And then you have this thing which is bounded. That's the sort of singular integral theory part, the T of 1 theorem applied here.
Okay, I understand. Thank you.
And what with weakly pseudo-convex domains?
Here's the problem. If you want to talk about minimal smoothness, then in order to talk reasonably, let's say of a weakly pseudo-convex finite type, you basically involve the type. You basically have to have a higher degree of smoothness to talk about those. I mean, I just don't know. I mean, we don't have a definite proof for this, or even a formulation of why, in what sense it's sharp. But when one thinks of these weakly pseudo-convex domains and one does analysis, they usually have some kind of finite type. And that really, even just to express or use that, requires a degree of differentiability which is higher than C2. So if you want to stick to C2, which is what we're sticking to, it's but I agree there's nothing, it's just sort of vague.